So I want to evaluate this limit 3 different ways. We're going to evaluate it graphically, we're going to evaluate it numerically, we're going to evaluate it analytically or algebraically. Graphically, what are we going to do? How do you think we could evaluate this limit graphically? So we're going to look at this on the graphing calculator. I want you to graph this function right here. And I want you to type it in exactly as is. Don't try to simplify or anything, just type it in like that. So we're going to look at this function, and we're going to look at what happens when we take x values close to 1. Hopefully you got a graph that looks something like this, right? Okay, good. It looks like a line, right? So we know a little better. This isn't just a regular old line, but what's going to happen with this line? There's a hole in it, right? So there's a hole. You can't see it here, but we have x minus 1 in the denominator, so we know that what number is not in the domain of this thing? 1. So we know there's going to be a hole at x equals 1, which is going to be right here, right? Now, your graphing calculator probably does not show that hole. There's a really, really good chance that it doesn't show it. My computer doesn't show the hole. So what we want to know is what happens as x gets close to 1. We know that x cannot equal 1. But we can see here that as we approach it from the left side, and as we approach it from the right side, the values of this function are getting really close to what? Okay? Now, can you try this? Hit the trace button on your calculator. Some of you may have tried this already. And type in the value 2. What does it say? Invalid? Oh, I'm sorry. Type in the value 1. My bad. We want to know what's happening as x approaches 1. So type in the value 1.
Nothing there.
If you did what I told you to do, it should have been 3. So you type in 1, what does it say? It actually depends on the calculator. I think some of the calculators do different things. But it's either going to say invalid, or it's just going to be blank, or it might say error. Why? Because there's a hole there, right? Okay, try this. Type in 1.00001. That's pretty close to 1, right? I don't know how many zeros I said.
3.
Okay. What's it say now?
2.0001.
Okay. What do you think is going to happen if we put in numbers even closer to 1, like 1.000000001? It's going to get closer and closer, right? So let's just imagine that we filled in this hole here. What would we fill in if we had to put a value in for 1? We'd put 2 in, right? So what do you think the limit of this function is just by looking at the graph? 2. Okay? Does that make sense? So basically, by filling this hole, we can evaluate this limit. Now, we don't have to fill the hole. We can see on the graph that the values are approaching 2 from the left, and they're approaching 2 from the right. And it's kind of being squeezed in between them, which is nice too. That helps. We know that anything to the right of 1 on the x-axis is going to give us a value just a little bit bigger than 2. And the other way, a number less than 1 is going to give us a number a little bit less than 2. All right? So let's look at what happens numerically. Means that we're going to look at the numbers. What's happening when we get close to 1? We don't really care what happens at 1. This limit right here, the whole idea of the limit is x is never actually going to equal 1. It's just going to be close to it. So what I want to do here is make a little chart. And you guys have already done some of the setup work in your calculator. It's going to make this really easy. But I'm going to make a chart here in xy or x f of x. And I want to know the values here. I'm going to choose values that are getting close to 1. So on the left side, getting close to 1, I might say 0.9. Should probably put that in the x row. So I'm going to put in 0.9 for x. I'm going to put in 0.99. And I'm going to put in 0.999. And then on the right side of 1, I'm going to put in 1 point, well, I'm going to start with the closest one, 1.001, 1.01, and 1.1. So I'm going to put these values in for x and see what this function spits out for us. Now you can do this a couple of different ways. If you go to the graph and use trace, that'll do the work for you. Or you can go to your table and it'll do most of the work for you. You can enter the values for x and it'll give you the values for y. You can do it either way. Go ahead and do that and figure out what each of these are going to be. Just looking at the numbers here that we get for this, as we approach from the left, we're at 1.9, then we get closer 1.99, we get a little bit closer 1.999, and it's pretty easy to see that we're approaching 2, and not only are we approaching 2, but we're approaching 2 from just below 2, right? Which that type of information could be useful for us later on. And then on the right side, as we approach, we're at 2.1, then 2.01, then 2.001, and we're getting closer and closer to 2, and we're also approaching from above. I think it's pretty easy to see, and you can probably extrapolate here and say, okay, well, if I plugged in 0.9999, then I'm going to get 1.9999. So you can see that we're getting numbers that are really, really close to 2. And even though we can't put 2 in, we know that the closer the number is to 2 that we put in, the closer the number that is to 1 that we put in, the closer the number will be to 2 that we get out. Does that make sense? So looking at the numbers here, what would you say this limit's equal to? 2. Okay, now, both of those ways require a significant amount of work, whether it's typing it into your calculator, looking at it, understanding the graph. And this is a pretty simple one, but if it gets more complicated, then you might not know where the holes are, and you might not understand the graph completely. Numerically, obviously, was a lot of work because we had to, first of all, write this all out and then find the values for all these things. So the last one we're going to do is analytically, and I'm basically just going to show you how we can evaluate this limit. One method of evaluating limits is called direct substitution. And direct substitution is the easiest way to evaluate limits. It doesn't always work, though. And I'll tell you right now, it's not going to work here. But this is how direct substitution works. I'm going to take this value here, 1, and put it in for x, and see what happens. Well, what happens here when I put 1 in for x? What do I get? 0 over 0. 0 over 0 is what we call an indeterminate form. We don't know. We don't know what 0 over 0 is. It's what we would expect to get, though, because this is the slope formula for 2 points that are on top of each other. So we would expect it to be 0 over 0. So what we can do to evaluate this analytically is we can simplify this with the understanding that x is never going to equal 1. When we're taking this limit here, x approaches 1, but it never equals 1. So we don't have to worry about when the denominator equals 0, because it's never going to equal 0. It's just going to be close to it. Does that make sense? Okay, so this limit is equal to the limit as x approaches 1 of a different expression that's the same everywhere where x is not equal to 1. Which is what? X plus 1. And you can get that by factoring x plus 1, x minus 1. And in this limit, it's okay to cancel these out. And again, it's okay to cancel those out because we know that x is approaching 1, but it's never going to equal 1. And since this limit says that it's never going to equal 1, we don't have to worry about the denominator equaling 0. So we can cancel those out, and then we can say this is equal to the limit as x approaches 1 of x plus 1. Now just a quick notation thing. First of all, this expression right here is not equal to x plus 1. A lot of you will be tempted to write that at some point during your calculus work. Just leave the limit off. It's important that you understand that this limit is important because it's telling us what's happening with x. Another thing, if we leave the parentheses off, it's just like anywhere else that we have parentheses, that would mean that we're taking the limit as x approaches 1 of x, and then the plus 1 is separate from that. So if we're going to take the limit of the whole thing, we need to have that whole thing in parentheses. And we'll talk more about notation as we get into the nitty-gritty stuff here. But now we can use direct substitution. We can just say, okay, well, I know x is approaching 1, but I can also see what happens when x equals 1. Because if I put 1 in for x here, what do I get? 2. So we came about this answer 3 different ways. We looked at a graph. We could see that that graph was getting close to 2 as x gets close to 1. We looked at it numerically, and we plugged in values around 1, and we saw that that gave values around 2. And the closer to 1 we plugged in, the closer to 2 we got out. And that's a key there. That's really important. As you get closer to the x value, the numbers should be getting closer to the limit. And then analytically, this is what we're going to be able to do with all of these, because I said when we're dealing with instantaneous rate of change, what kind of discontinuity are we going to have? A removable one. So we're going to be able to remove those discontinuities and then just plug it in.